Right. So if you want to have a reconstruction, okay, so these are stored in the computer. Now you want to retrieve the song or audio. What is that you have to do? We have only samples. So these samples our ears cannot hear. We want a continuous time signal. Indirectly, it means we want x of t back. So if you want x of t back, what does it mean? Where is our x of t? In time domain, it is x of t. In frequency domain, it is our x of j omega, where that fellow is centered where? That fellow is centered at origin. So these fellows, these replicas, okay, they don't give me the original signal x of t. Okay, so where is my Fourier transform of original signal concentrated? It is concentrated at origin, and I want only this part. So if you can extract this part, then indirectly it means in time domain you are extracting your original signal x of t, except that that is scaled by a factor of 1 by t, which can be compensated by passing the reconstructed signal through amplifier. Okay, right. So I repeat again. So the sampled signal xs of t, which is stored inside the computer, is having the periodic replicas of original Fourier transform x of j omega, but our original signal is x of t. To get back your x of t, you should get back your x of j omega, which is what? Which is centered at origin in excess of j omega. We want only this part. We don't want all these guys. We want only this part. If you can get that part in frequency domain, indirectly you are getting the corresponding x of t in time domain. So we will talk about that a bit later. Yes, but what is the first thing you should take care? What is the first thing you should take care of? These replicas of Fourier transform, they should not cross over with each other. If they cross with each other, what will happen? Where even at the time of reconstruction, we cannot get back our x of j omega. Okay, so to get faithful reproduction, so faithful reproduction of x of j omega means what? You want to, from excess of j omega, you want only x of j omega. Okay, there should not be, okay, so there should not be overlap of spectra. Okay, so these fellows should not overlap with each other. Overlap of spectra. Okay, there should not be any overlap of the spectra. So when will this overlap doesn't happen here? When this point and this point are not crossing with each other. Okay, so this happens. When will this happen? This happens only if, can you tell me the condition here? This point is how much? 2 pi by t minus 2 pi b. What is this point? This point is 2 pi b. So we want 2 pi by t minus 2 pi b to be greater than 2 pi b. Okay, this happens only if 2 pi by t minus 2 pi b is greater than, we can put equal to, correct? So it should be greater than or equal to 2 pi b. Why? If the points touch each other, still okay, theoretically we can get back that Fourier transform, but if they cross each other, then we cannot get the Fourier transform. Okay, yes, so this implies, so on both the sides 2 pi is common, so this implies we get 1 by t minus b is greater than or equal to b, or 1 by t is greater than or equal to 2b. So overlap of spectra doesn't happen only if 1 by t is greater than or equal to b, and this is the sampling theorem. Okay, yes. So what is that we want? See, for faithful reconstruction, we should not want any overlap. So, and for that not to happen, these 2 points should not cross each other. Indirectly, it means the second point should be greater than or equal to first point, which is nothing but 2 pi by t minus 2 pi b greater than or equal to 2b. because pi 2 pi is common on both the sides, we can cancel it. You get 1 by t greater than or equal to 2b. But what happens if this condition is not satisfied? We'll talk about that. Okay, sorry for that. We will talk about that later. Okay, so this that we'll put in words, that is, what is 1 by t here? T is what? T is period of our periodic impulse train. So 1 by t will give you what? Number of samples per second. Okay, so 1 by t will give you what? Number of samples per second. Okay, number of samples per second should be greater than, correct, number of samples per second should be greater than or equal to, greater than or equal to twice the bandwidth of the signal. Okay, so twice the bandwidth of the signal. Okay, so for faithful reproduction, the Fourier transform should not overlap with each other, and for that to happen, the above condition should be satisfied. That is what? The number of samples in 1 second should be at least should be greater than or equal to 2b. If this condition is satisfied, then what will happen? We can get back that x of j omega, which is centered at origin, right? So this x of j omega, which is centered at origin. Okay, so we can get back that. So once we get back, so we can have the analog signal x of t. That's what we mean by faithful reproduction. So what is the requirement? The number of samples in 1 second. Okay, number of samples in 1 second should be greater than or equal to 2b, where b is the bandwidth of the signal. So if this condition is satisfied, we can get back our x of t without any distortion. Okay, if the above condition is not satisfied, okay, I'll talk about that again, sorry. Okay, so this is called sampling theorem. Okay, so this is called sampling theorem. Okay, so let us write down in a formal way. Okay, same thing, we will, whatever we have seen above, we will put it in a nice way. Okay, so what is that? If x of t is a band limited signal, okay, if x of t is a band limited signal with a bandwidth of b hertz, okay, with a bandwidth of b hertz, then we can reconstruct, correct, so then we can reconstruct x of t from its sampled signal, from its sampled signal x of t, xs of t, right, sampled signal xs of t, provided it is sampled, if provided it is sampled such that the following condition is satisfied, such that the following condition is satisfied, such that the following condition is satisfied. Okay, what is that condition? 1 by t should be greater than or equal to 2b. So at least how many samples you want in 1 second? 2b samples. Okay, note that you and this we will write down that at least you want 2b samples. Okay, so 1 by t is called sampling rate. Okay, is called sampling rate. Okay, its units is what? Number of samples per second. Okay, its unit is number of samples per second. So sometimes they call it hertz, but yeah, so we should be careful. The units of sampling rate is what? It is samples per second. Okay, number of samples per second. Okay, and what is the unit of B? B is hertz. 1 by T units is number of samples per second. Okay, sometimes they call sampling rate also in hertz, but let us avoid that. If they use it in gate exam, that's okay, but still we will use number of samples per second. Now the threshold value. So the threshold value, what is threshold value at? So threshold value 1 by T equal to 2B, correct? When 1 by T equal to 2B, what happens? The Fourier transform just touch each other. So the threshold value 1 by T equal to 2B is called Nyquist rate. Okay, so Nyquist sampling rate, or we'll say Nyquist rate. Okay, so 1 by T equal to 2B is called Nyquist rate. Same Nyquist, what you have studied in control systems, right? Same guy. So it is called Nyquist rate. So now what happens? See, for these two cases, no problem. Which cases? 1 by T greater than 2B, faithful reproduction is possible. 1 by T equal to 2B also, theoretically faithful reproduction is possible. But what happens if 1 by T is less than B? Okay, if 1 by T is less than 2B, then what happens? Then the spectra, correct? So then the spectra of whom? Then the spectra of XS of J omega overlap with each other, correct? So overlap with, will overlap, we'll just keep it like that. So we'll overlap, and we cannot get, x of t back. Okay, so we cannot get x of t back. So indirectly it means what? X of t will get distorted. So we get, or what do we get? We get a distorted version, okay, or some different x of t. Okay, so we get a distorted version of x of t. Okay, okay, yes, so we get distorted version of x of t. So this overlap of spectra, we call it as aliasing. Okay, so this overlap of spectra is called aliasing. Okay, so it's called aliasing. Okay, so that's okay, but what is the requirement here? So if you want to have a faithful reproduction, what is the condition? Our sampling rate should satisfy the Nyquist criterion. So what is that? 1 by T should be at least equal to 2B. If it is greater than 2B, no problem, but at least it should be equal to 2B, and this we call it as what? Sampling theorem. Okay, so this is proposed by Nyquist and Shannon and Kotelnikov. So all the three guys contributed for sampling theorem unknowingly. At the same time, they were working on the same topic in different countries. Nyquist is from Hungary, Shannon is from US, and Kotelnikov is from Russia. So almost at the same time they were working on the same topic. So that is coincidence. Okay.